Today in this video we will discuss equilibrium again, but now it's going to be the equilibrium of a rigid object. Equilibrium. Okay. So let's consider this rigid body is a potato chip, and it's being acted by this external force. So if we want equilibrium, as we saw in an earlier video, we need that all the forces external together, they need to be equal to zero. So there is no total acceleration, there is no net acceleration. But this is a rigid body. This is not like in chapter 5. Now the body is not a particle, it's an extended object, and that force will also generate torque. So, but if we want this thing in equilibrium, then we have to make sure there is no translational motion, there is no translational acceleration, and we also need to make sure there is no angular acceleration. Right here we want the translational acceleration to be zero, so we need no external force. So in order for the angular acceleration to be zero, well, we need the external torque, net external torque, to be zero. And that's it. These are the two conditions that need to be met to have a rigid object in full equilibrium. No net force, no net torque. You remember you have the static equilibrium scenario, and then you have also the dynamic equilibrium, in which here, when it's a static, the velocity is at zero. Here, the velocity is not non-zero, but still constant. Of course, because there's no linear acceleration. And the same thing for omega, right? But constant. So we're gonna talk about static equilibrium mostly, just to make sure to understand the difference between the two equilibrium conditions. That not because there's no force or no torque, total external, that means the velocity has to be zero. When you're in cruise control, when the car is moving at constant velocity, but the total forces are zero, but there is still velocity. Same thing, something can be subjected to zero torque and still be moving. Consider this first scenario. If you add the forces, you're going to have sum of forces equal to zero. This force here cancels with each other, with this other, so they cancel each other out. So you have a static, you have zero translational acceleration, but here generates pure torque. So the sum of torque is not zero. The second scenario is different. We can clearly see that the sum of forces is not zero. But what about the sum of torques? The sum of torque, with respect to this point, which is point A, let's say, is zero, right? You see, no force has any lever arm with respect to the point. The thing is, if the sum of torque about a point gives you zero, then the sum of torque about any other point is also zero. I mean, if these forces act this and here, and they don't make the peanut rotate, they won't make it rotate about any other point acting together, right? So there you go, an interesting scenario. In this case, the peanut will move, will have translational motion, but no rotational motion. In this one, we'll have a rotational motion, but no translational motion. To fully have equilibrium in an object moving in the XY plane, then you're going to need the forces in X to be 0, the forces in Y to be 0, and the torque to also be 0. You need all three conditions to have a rigid body fully in equilibrium. Another additional thing that I want to remind you is the concept of center of mass, which we say, for instance, for the x-axis, the coordinate of the center of mass in the x-axis is just adding all the masses times the position over all the masses, right? So, and then the same thing for the y-axis. Well, what I want you to notice is that if the body, the rigid body, is homogeneous, so the properties are the same in all directions, like for instance the density, and gravity acts uniformly, then the center of mass is also, when you calculate where gravity acts on each mass, the center of mass is also called the center of gravity, but only if the body is homogeneous and gravity acts uniformly. So the position of the center of mass is also the position of the center of gravity. So we can assume, basically what I'm telling you is, we can assume that not only the whole mass of the object is located at the center of mass, but the whole weight is located at the center of mass, which we call also the center of gravity. So let's take a look at this example again. Is the seesaw we did in a previous video. So we know the mass of the father, the mass of the daughter, and we know the location of the father is D, the location of the daughter is L/2, so half the length of the plank, and we know the weight of each one of them. So first, determine the magnitude of the forward force, the normal, exerted by the support, which is called the fulcrum here, right? So we can just do a free body diagram. We can do the free body diagram on the the board, right? So what forces act on the board? Well, the board feels its weight, so we're going to do a sum of forces in Y. We're going to have minus mass of the board times gravity. It feels the weight of the father minus the mass of the father times gravity, feels the weight of the daughter, mass of the daughter times gravity, plus the normal, right? And the seesaw is not moving up and down. It might be rotating, but we don't know that yet. With the sum of forces in Y, all we can find is the mass, and here very importantly, I will need to write here mass of the plank, because this is the free body diagram of the plank or the board, so big M. So that will be the acceleration in Y. But this, we know, doesn't move up and down, so this must be 0. So then that means all of this is equal to 0, and the normal is simply the father weight plus the daughter weight minus the plank's weight. And that's it. That's the answer. You can put it. Father, daughter, board times gravity. That's the normal. Okay. And we simply know, well, the normal is compensating for the other 3. And there is a mistake here. This should be negative. Right. So plus, there you go, plus. That's right. That's what it needs to be. Negative is going down, the weight of the board. And now it says, determine where the father should sit to balance the system at rest. So that means rotational equilibrium. Equilibrium. That's what we want. And that means the sum of torque about 0.0, we're going to call it 0.0, and truly about any point has to be zero. But, we have to choose a position to measure all the torque. So that's very important. The torque about any point in the universe, not any point close to the fulcrum or any point on the board. To have rotational equilibrium, the total torque about any point in the universe, right, should be zero for with respect to the body you are analyzing. So that means you can put the origin wherever you want. You can put it here, 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 you can put it down here. It doesn't matter. The torque has to be zero about any of those points. So for simplicity, I'm going to choose the center of the board. And by doing that, I'm going to calculate the torque. So we're going to have the contribution of the father. And you see, the father alone will make the seesaw rotate like this. So positive. So it's going to be positive. Force of the father, which is the weight, times the radius, or d, the distance d. The other force is the normal, but has no lever, and the mg also do nothing because they're acting directly at the pivot. So then we're going to have the daughter, but the daughter tries to make the system rotate in the opposite direction. So the mass of the daughter times gravity times L over 2. And these two together need to balance. They need to cancel each other out. So together, they give you 0. And this tells you where the father needs to be sitting. It needs to be sitting there. Well, at this location. If we had numbers, here we plug the numbers and we will know exactly where the father needs to sit to make sure the seesaw doesn't rotate. And that's it. That's chapter 12. We are going to do more complex problems in class. See you then.